Okay, so then thank you for staying, and I think we open up the discussion session for questions for all the speakers. I think only 2 of the speakers are here now, right? I think Sylvain couldn't stay, right? So he had to go. So you can reserve questions maybe for via email or something like this, but Misha and I are here, so please feel free. We have the microphone. Yeah.
Okay, I have a very simple one for you, Carlos. So can you explain a bit more where your massless helical bosons come from? Because I totally missed this point, and I think that was one of your main stories.
So the massless stuff is the usual thing. It's just linear dispersion, right? So there's no, if you think about relativistic particles, they have a mass. In massless case, it's just the case that there's linear dispersion. Your
excitations quasi particles is sound. And
yeah.
Sound has a linear dispersion. A linear dispersion is massless.
Yeah.
I think that's all about it.
That's all, yeah. But then he's asking the other point, which is just the helicity thing. Where does it come from? It comes from the spin orbit coupling, which you know, if you think about, you remember that I said there was this effective magnetic field, H effective, which has a X component, let's say, and a Z component. It depends on K. So as you change K, your Z component is changing direction. I mean, it's not changing direction. Your Z component is increasing with K, positive and negative. So it's proportional to the momentum of the electron. And your X component is fixed. So when you look at the field, what the field is doing is just rotating in K space. So that gives you a helical structure. And that helical structure sort of translates into the bosons, because the bosons are reflected as some kind of product of this fermion states, the density, modulation for individual spin, and that helicity translates into that. It cannot disappear. So the point that there's helical structure is just coming at the end of the day because you have spin-orbit coupling. And that's why when the spin-orbit coupling goes away, you just have your standard charge density wave and spin density wave. There's no helical structure there.
I have one question to Misha about sort of the PXP model. Sort of, there one basically says I focus on just sort of the nearest neighbor exclusion, and the long-range part is not that is not important. I mean, are there situations in which this becomes important, and are there certain effects that are associated with that?
Yeah. So it definitely, it's this PXP model is certainly an approximation, and for example, let me see maybe some. So it definitely, for instance, even in this 2D.
Excuse me, can you use the microphone?
Yeah. No? Yeah. So, for example, the phases. No, sorry, it also kind of in this phase diagram, which is you see the traces. I mean, certainly PXP model would not describe something like straight phase, right? Even in 1D, there are sort of different phases and so on.
There is,
exactly. There is exactly. So one has features. Yes. So there is absolutely, and for example, also, for more complex lattices, often for example, the question about this ground state for this spin liquid in a Kagame link model. If you have PXP type Hamiltonian, it's very clear that this RBB state will be a ground state. But if you start, for example, looking at these tails, things start to matter. So it is a nice model. The reason why it's nice is because, for example, if you use PXP model, you can actually truncate your Hilbert space and simplify, for example, numerics. But it's clearly, it's an approximation, Yeah.
And so in a very related question is, I mean, sort of in a way, if you look at sort of in this Kagome situation, you have these dimer coverings. I mean, can you sort of in a way that's a counting problem here? I mean, can you, I mean, to which size or so can you in a way in practice do such a counting here? Or?
You can, I mean, like you can count a number of this dimer cover. It's an, you know, there is an exponential number, of course, of this, you know, so counting in what sense? Maybe I don't completely understand.
Well, I mean, like, of course, I don't know. I'm not an expert on that, but I think sort of in a way the counting of dimer configurations on whatever non-trivial lattices is, I think, an unsolved problem.
Oh, the question, can you use it to...
Can you use it sort of...
I see.
This is the direction.
Yeah, it is, yes. It is actually, it turns out that it's, I think it's subclass of what's called maximum independent set problem. So basically, you can map, like if you have this hardcore precise constraint, you can take any graph in 2D and basically, you know, and like for this like sharp blockade constraint, you can actually show that the kind of the classical, in the kind of classical limit, in the limit of large detuning, the ground state of this blockade problem is actually a ground state of something which is called maximum independent set. Okay. And this is, it's a graph problem where you basically, it's sort of, it's almost like this is, you know, conclusion is almost trivial because so basically what maximum independent set is that, so you have some kind of vertices and you can, you know, connect them with edges, and then it's a kind of a coloring problem. So what you would like to do, you would like to, you know, color as many of these vertices as possible, but you cannot color two vertices which are connected by the edge. So it's a well-known problem in computer science called maximum independent set. And it's in general, it's an P hard problem. So for this kind of blockade problem, it actually maps into some subclass of this maximal dependent set. It's called unit disk. So a unit disk means that you just connect all vertices which are within certain disk. It's kind of a blockade. It's almost by definition. So this unit disk is also to find exact solution is NP hard. There are actually algorithms for approximate solutions which are efficient. So it's in principle, if you can find, if you can do adiabatic evolution and create these states, you know, you could solve this class of problems. So we actually studied it, and for some classes of problems, and in fact we found that, you know, like this adiabatic evolution with this Rydberg Hamiltonian results in a speed up, in a kind of a quadratic speed up, compared to classical Monte Carlo, but also even compared to quantum Monte Carlo. But of course there are other algorithms which are classical algorithms, kind of heuristic algorithms, which are much better. So it's sort of not, and like to be maximally honest, to really find definitive solution, you kind of need to go to larger systems, and there it's like not so clear if we have enough like circuit depth to really read, because you need to make sure the correlation spread. But it is actually ongoing topic of research. Yes, yeah, exactly. But actually, so the interesting thing is that the places where, like, okay, our conclusion, the places where this adiabatic dynamics really helps are the situations where you have small number of optimal solutions and large number good but not completely optimal solutions. And it's because in this case classical algorithms actually get stuck in this. So in that sense, this Kagame problem, I mean, you have a lot of optimal solutions. So it's not like, this is not a good example. I mean, usually you need some kind of disorder and so on to make it hard. I mean, it's not hard to find for the Kagame, but yeah, anyway, yeah. It's an interesting connection indeed. Yeah. Yeah.
Okay, so question, Yvonne?
I don't know if this question was asked already because I arrived late, but the question to Carlos. So in your bosonization procedure, you actually linearized locally the dispersion relation of the three fermions.
Yeah.
So this is an approximation, right?
Yes.
So can you comment on that? What are the consequences if you go beyond that approximation? What happens?
Okay, so
What survives to
yeah,
an exact treatment?
Well, yeah, it's a long wavelength approximation. So even without any spin-orbit coupling, spin-charge separation would only happen essentially asymptotically at a very low Q, because that's only when.
I disagree, honestly, because we did numeric simulations. I mean, okay, I not personally, but I mean with Corinna Collett and so on, we found that this is pretty robust. So you don't have to go to this extremely low energies, whatever stuff and so on. Spin charge separation is a pretty robust, I mean, at least in this trivial sense that sort of you get these two independent sort of velocities which differ. In this sense, this is pretty robust. And so, I mean, of course, ideally you argued like you make this linearization, which actually only works for long range potentials, because I mean, if you have short range potentials which have high momenta, of course, then I mean, your interaction sort of violates that linearization very easily. But, I mean, from numerics, what we found is that the spin charge separation is pretty robust. Even for short-range interactions. I mean, we did, with Corinna, we did these calculations on the Bose-Hubbard or Fermi-Hubbard model and things like that.
So what happens when you have very strong interactions? Because here there are two problems. There is the linearization approximation.
And interactions are
first,
weak enough.
and second, that you linearize around the unperturbed fermion dispersion relation. So if you have very strong interactions, this can, to some extent, distort. So
the answer is that, I mean, the problem is sort of in a way well behaved. So it doesn't, even for strong interactions, I mean, it's...
I would not be so...
With velocities which are sort of renormalized. So, of course, you cannot take the bare ones.
But then in this case, which one do you take if you don't take the bare one?
Well, then you can only sort of in a way see that there's two independent velocities and they scale with u or something like this. Well, I mean, there's a dependence on...
So you mean that you are not able to predict the value of the velocities? You are not able to predict the value of the...
It's so long ago that I don't remember all the details, but I think this is pretty robust.
Yeah.
My remembrance. And yeah, okay, one should look up.
I would disagree a little bit.
Is there a way to go
so
beyond that approximation? For example,
Yeah.
you found a linear spectrum, but in reality...
Yeah, for instance, I know, I think there's a result probably by Michael Postunek also on the 1D systems. If you go beyond the linearization stuff, you start having mixing of spin charge. But mixing, so they're not anymore the right eigenmodes. So you're still going to have two different velocities, that we're not debating, but they're not going to be spin and charge. There'll be some kind of coupling between spin and charge modes.
I mean, the problem has been discussed in a lot of detail by Leonid Glasman from Yale, and he has predicted sort of in a way universal things beyond sort of this linearization features. But this is also some time ago, and I don't remember the details, but I mean, if you look at Leonid Glasman,
it's probably the same group of people. Michael Postunek is my colleague at Georgia Tech. So there will be two velocities. This we're not debating. We're debating the issue of, are we going to call that as spin and charge separation? There'll be two modes, but they're not going to be spin mode and a charge mode. Okay, so the two modes is not an issue. It's what there will be some mixing.
There is some admixing when that tends to 0 and Q tends to 0.
And then spin charge separation happens. But you're always going to have two modes.
I haven't really thought
charge separation, as long as you put in an interaction only between spin up and spin down, will you actually have the separation that one mode is only a density mode and the other mode is involving spin?
Yeah,
because you would
as long-
say,
as you
if
said
you're
that-
not trying to separate spin up from spin down, if you just create a density mode, you leave spin up and down, interacting as they do. So I'm wondering, when does the character of the modes really change as a function of interaction between up and down?
Yeah. What the interactions do? If you had Coulomb, for example, you're going to have different velocities in this linear approximation, low q equals to 0. So in the Coulomb problem, which is going to, all the spins, density, up and down, all enter. You're going to see that you have more contributions, but as long as you have sufficiently long range, there's a certain range of interactions which you can throw away the high momentum transfer. There will be spin charge separation, but the velocities will be different from the Coulomb case and for the up and down case. Because in the Coulomb, you're going to have four types of interactions that show up, while here you have only up and down.
Let me add the question, why, to what extent is spin charge separation important? I mean, is it something which people have figured out and it was sort of a nice, finding in one-dimensional physics and people wrote a bunch of papers about it, but is it still a current challenge and frontier? Or is it sort of checked off?
I don't know. I mean, you want to answer? You want to say something? No. For me, my interest on that was not so much on spin charge separation. Although I think in the cold atoms community there were some papers recently by Hewlett.
Randy Hewlett together with Thierry Cimaki had some papers where they saw there are two different speeds of sound, so to speak. They observed the phenomenon.
Exactly.
And based on that and your talk today, I was just asking, should I, as an experimentalist, think more about spin charge separation? Is it something important, or is it something which is sort of peripheral interest?
Curiosity. I don't know. When I first learned that as a grad student, I always thought it was just a curiosity for me. Maybe other people that have worked their lifetimes on spin charge separation, this has been already understood and thought of since the 60s. So it's something that, in 1D systems appeared as sort of not a big surprise. When I went into this business, I was saying, okay, we have that. Okay, so I'm interested in knowing what happens if I add spin-orbit coupling to the system. What happens to those spin charge separated modes? How do they mix? You expect them to mix. How? Is anything special? And the two little things that we found was, as you expect, of course, you have these two modes, they're mixed. Spin-orbit helps them mix and mix in some special ways. And you have these transitions, which are topological, between 4 Fermi points, 2 points, and so on. So you lose one of the modes. And one thing that I didn't talk about was when in the less case, when the Fermi velocities are opposite each other, the modes actually, you have two modes, and one of the modes has a positive chirality with its counterpart which has negative, and the one and some other mode which has some weight from the negative Fermi velocity stuff has the opposite chirality of the other mode. So in principle, when you go from n equals to 4, where the two Fermi things have the same velocities, they have the same chiralities. So if you can do a Bragg scattering experiment, you can detect chirality, and you can see the chirality between these two n equals to 4 fermion states. They are different. So that's one curiosity out of that. But from my perspective, I mean, you may know more about stuff. It's something which is very old.
Many-body theory that, in a way, for decades had not been experimentally been realizable. But of course, one has to say that in a much more detailed way than one that has been done by Amir Jacobi in Harvard with these edge states. So Amir Jacobi and also together with Bert Halperin, they analyzed sort of spin charge separation in edge states very nicely, and in a way far beyond this just that you have sort of two separate velocities. They really were able sort of to, in a way, measure the spectral functions. that there are separate spectral functions for these two type of excitations. That's something that's very sort of exciting. But I mean, okay, this is already also some time ago now. At the moment, I mean, Immanuel Bloch and they had, I mean, a few years ago or 2 years ago, some experiments which also showed it, but I mean, not perhaps in this, I mean, to the level of sort of, I mean, sophistication that Amir Jacobi has done in the condensed matter context.
And then I ask you a question, because if I remember about the Jacobi, they were experiments which they actually see them as quasi-particles, right? Not as spin density, charge density waves, which is a collective thing, but as holons and spin-ons, right? Which is a bit more difficult to
No, I mean, as far as I remember, the experiments by Amir Jacobi, they were sort of in a way with this tunneling. This is you measure sort of essentially the tunneling density of states. Tunneling density of states is really the imaginary part of the one particle green function, and then they really could map it out both as a function of frequency and momentum. So this is fantastic. So,
but in the single particle sector, here we're talking about the density in the spin density sector.
yeah, but I mean, sort of they also.
There are different flavors.
Yeah, okay. I have no. It's an old story.
So there's the spin star separation school of Phil Anderson, in some sense, in which he talk about. Imagine that we have some very strongly correlated systems in which you can decompose your fermion as a boson times another fermion, and the fermion carries the spin, and the boson carries the charge, and then we can do some theory and say, okay, this is really a quasi-particle type of spin-charge separation. While here, it's not really a quasi-particle type of so there's quasi-particle spin-charge separation that may exist also. And that was Phil Anderson put, which is slightly different paradigm.
What?
Here, it's really spin-charge separation in the sense that the spin density, the charge density would propagate at different speeds. It's not that the electron fractionalizes into a spin-on and a holon, and the holon has a charge, it's a boson, and the spin-on has only the spin. So it's a different type of paradigm. Okay. One is a quasi-particle type, and the other one is a collective mode type. But you know.
Can I add a question to spin-orbit coupling? The simple Raman momentum transfer scheme which you described, one-dimensional spin-orbit coupling, of course that's what you need in one dimension, but if you want to go to higher dimension, this special scheme with just two Raman lasers is of course this superposition of Rashbach and Dresselhaus coupling,
Yes.
and is usually regarded as trivial because it does not involve non-commuting operators. So therefore, for many phenomena related to spin-orbit coupling which have been explored in real materials, the simple Raman scheme is not sufficient.
No, but wait. If you're talking about non-abelian gauge, I mean, you still the sigma x and the sigma z components, they do not commute, but they are not really a non-abelian gauge in the sense that of the Rashba would be, because you have both of them has a momentum.
Anyway, maybe I want to sort of just lead to a question.
Okay.
Since you talked here about as an open question and open frontier to put in spin-orbit coupling, do you want to make a few comments? What would be maybe important goals in higher dimensions?
Well,
Partially also because we have now, with lanthanides and atoms which have very high angular momentum, we have actually now different atomic systems which provide new opportunities to put in spin-orbit coupling schemes.
Yeah, I mean, one thing that I particularly like, which is actually interesting, if you are willing to, if you are willing to also change the sign of the interaction. I'm very fond of superfluidity, right? So one thing in principle we can do, let's say if you go from 1D to 2D and move from the paradigm of spin charge mixing and all this additional collective modes, and say just ask yourself the question about what kind of superfluid states can you have, for instance, if you have an attractive interaction. You can even stay with 2 components even, or you can go to higher components, which even more exciting, I would say. But the key point here, I think, is that once you introduce spin-orbit coupling into the system, of course you modify your kinetic energy. That's exciting. Let's say if you have SU2 or SU3 invariant interactions, you don't do anything to the interactions, but you can do the other way around. You can just say, look, let me look now into the diagonal bases, the bases of the dress states that result from the spin-orbit coupling. And immediately what you see by doing this rotation, diagonalize the kinetic energy and look how the interactions look. You can immediately see if you only had S waves scattering to begin with in the original basis, you immediately introduce higher partial waves. So that's why, in ordinary spin-orbit coupling systems, let's say in 2D or 3D for SU2, once you introduce it here, Rashba type, which can break time reversal symmetry, or ERD equal Rashba-Dresselhaus, which is the one-dimensional version of that, you can introduce P-wave components. So it was a route. In fact, I went into this business for the fermions because I spent a lot of time in the past trying to get the P-wave stuff. I remember a phone conversation with Debbie Jean when the BCSBC stuff, because we were at the same general area. She said, oh, we're getting something like BCSBC like you have done when you were at the time in Illinois. And I said, well, but Debbie, this was very boring because you should be looking at P-wave. You have a quantum phase transition P-wave. And of course, she tried those experiments, and the lifetime was very short. So then immediately when a few years passed, I thought, well, maybe a route to P-wave would be to use spin-orbit coupling. So we wrote several papers early on that issue, which didn't happen also because it requires fermions. And the fermions, the lithium case, for example, the old ones, heat up. Potassium doesn't work so well. Ytterbium, not clear. But yes, the new systems with higher spins and higher components, I think is very interesting. In fact, for the SU3 case, which I had as a backup plan, you would see not only P-wave showing up, but because of the SU3 nature of the interactions, you're going to have, even if you start with S-wave, color-like interactions, S-wave between 2 different colors, you end up with singlet, triplet, and quintuplet channels which show higher partial waves showing up. So one thing that I think is interesting from my perspective is that playing with spin-orbit coupling allows you, in principle, to explore higher angular momentum interactions just by going to the diagonal basis of the spin-orbit. So it immediately emerges, and you can see higher order. The order parameter has more nodes. You have P-wave, D-wave, F-wave, and the larger the system, the more partial waves come.
Yeah, I have a question about the quantum simulation and the adiabatic protocol procedure. This adiabatic procedure is always a trade-off between decoherence, where we want to have the sequence the shortest as possible, and adiabaticity, where you want to be slower. Do you think that it is intrinsically limited to small system sizes due to this problem, or are there ways to counteract on this effect and maybe I don't know, compensate decoherence or use a mixed approach with digital analog computers? What's your feeling about how we can extend this procedure to large system size?
Okay, so some of these things are kind of fundamental. For example, the fact that, let's say in the second order transitions that, the gap scales in a certain way with the system size.
Yes.
That basically, so you could kind of, let's say for some phases, it's very clear that you need to somehow propagate the correlations across the entire system, right? And whereas maybe you can actually improve performance somewhat. So, for example, Tolle is a big fan of this counter diabatic, things which actually could be useful, but some of these things you can at least, like in terms of scaling, you can maybe improve factors. Okay. You will have to, as the system size grows, you just need to spread the correlations. However, there are sometimes other ways to prepare interesting phases, and so what you can do, you can sometimes, for example, if you want to prepare some kind of exotic state, what you can do, you can actually first prepare, let's say, some kind of fancy topological state. You can sometimes prepare the state which is not as fancy by doing things like measurements, by using like stabilizer measurements, for example. So if it's like and then, of course, you could use that as a starting point to create some interesting state. So that actually circumvents, at least some of these things. So, and I think some things like this could be actually very interesting. So it's in this kind of era in between like full error correction and maybe kind of intermediate. So you can start already use other tools. And for example, like a toric code, usually you have, like the stuff, what we have done is equivalent to toric code. There it's a second order phase transition. There is certain scaling. If you do adiabatically, you have to do it for this kind of long time. But at the same time, what you can do instead is what I was talking, you can just measure stabilizers. It's depth one circuit, right? So you basically measure stabilizers. You just need to forward and correct, fix wrong stabilizers. And of course, in this case, you prepare the state, which is very simple. It's basically there is zero correlation length state. But for example, if you want to explore, there is not. You can learn everything about this state without doing an experiment. But what you could do, you could, for example, use some of this, like prepare some simple states which have topological order, and then sort of move to the domain which is actually not so easy to simulate. So something like this, I think this would be very exciting. That's very exciting possibilities. Then of course there is counter diabatic.
How is it what you said is different from counter diabatic? Because in a way, in a way, counter diabatic is a buzzword. So what you're saying is, what's your starting point? It's kind of part of counter diabatic.
Yes.
But then I would say, it's basically a trivial mathematical statement. If you follow a low entanglement state, which you almost have to do, because if you create whatever this crazy state, it will not be stable, then you follow counter diabatic by definition, but of unknown Hamiltonian.
Yeah, but but it's kind of the question here is, like, can you, for example, create certain complex states with the circuit depth which is kind of significantly shorter, and
I completely agree with that.
And parametrically short. And I think, for example, for some of these topological states, you have to spread correlations across the entire, kind of system, and you can either do it. And I think this counter idea, I don't think that's so these measurement-based schemes, they are kind of different because you spread information classically, right? You don't actually utilize sort of quantum.
But you do many measurements as you go.
Well, sometimes it's enough to do one.
No, but then I would say it's initial state.
Yeah, but you prepare highly non-trivial initial state from which you can sort of, but like how, preparing this initial state.
Okay.
Okay. Yes, yeah.
I'm sorry, it's a bit of an experimental question, but I believe in the 2023 December paper, you only perform one round of stabilizer measurement.
Yeah.
Do you believe the path towards continuous reloading mid-circuit measurement is straightforward for rubidium?
Yes. Any other question? But it's clear. It's a future. It's very clear. Yes.
So I know that I chair a session and I had to interrupt. Maybe I can ask one question to you. So you were trying to finalize your list did you manage to finalize your list of things on the challenges and opportunities, or there's something that in both columns will be easy and easy, because sometimes it's hard and easy.
Well, I mean, if it's easy with physical qubits, why would you do it
Yeah,
with
sure,
logical
that's what I'm trying to
qubits,
say.
right? It's,
But I mean, so those things will be you're thinking continuing that direction is
well,
the
I
way
mean,
to
it
go.
was, I mean, this table was a little bit, the idea was to have a little bit thought kind of provocative, and, you know, we yesterday talked with one-to-one, he's sort of like, I mean, I would say in the many body community, there is a healthy skepticism about this kind of digital approach, and particularly our corrected approach, being actually ever useful, right? Because people just think it's such a kind of, you know, high overhead, which kind of is true, you know. But things are kind of not, the point I wanted to make is things are not black and white, right? So,
yeah, but it's doing as well or better than the qubits for certain stuff and
well, this is true regardless of
that.
Right. You know. So, I mean, another question you might ask. So, okay, how do these atom approaches stack against superconducting qubits? Yeah. Which is actually also a very good question. And you know, I should say that, you know, just before going into that, you know, that like the progress that the superconducting community has made has been actually quite amazing, you know, just in terms of like improving fidelities and reducing errors and so on. But to be honest, you know, I do not see, you know, how they can really scale up these things. And it's, yeah, and it's, you know, I think people have not even started about this kind of even controlling these big systems, calibrating them, you know, is extremely challenging, you know. So in that sense, this control problem is actually solved here. So, but, you know, like you could actually make a comparison, you know, and, you know, things are not black and white. So, for example, what you mentioned is what people often, you know, criticize. They say, oh, these atom approaches are slow. And there are two things which actually are relatively slow indeed. One of them is this atom transport is relatively slow. The gates actually are quite fast, but the atom transport is slow. And also this mid-circuit measurement, which we need to usually use as a part of your error correcting cycle, is also like kind of like, actually right now it's more a millisecond, but I think 100 microsecond is realistic. So which actually is factor of 100 slower than superconducting qubits, you know. And, you know, this factor of 100 can be substantial because, you know, these computations you need to do are very long. However, you know, there are other aspects which one has to look, you know, for. And for example, one of the things which I mentioned kind of in passing is that, you know, usually if you use these architectures which do not involve these transversal gates, after each logic gate, you need to do d rounds of error correction to basically, you know, to circumvent noise in making stabilizers. So with transversal gates, you know, it turns out you can compile the gates in such a way that it's actually enough to have one round. And it's actually a big surprise to, I mean, there is a huge community working on this surface code in particular. It's actually a big surprise, but we see very clearly that this is like emerging as a conclusion. So the idea here is that you actually, what you can do, because the errors propagate in a deterministic way, so long as you keep track of that and then decode not just like qubits individually, but decode like the entire block, you know, which makes your decoding problem harder, but nevertheless, we still believe it's kind of trackable. I mean, you basically you save this factor of d, which at this point, the current speed of superconducting approach and current speed of atom approach become very comparable, you know. So of course, superconducting probably will speed up a little bit, you know. Of course, we also have to worry about this continuous reloading and, you know, also making maybe measurements in a little bit more clever way without, like, you know, destroying qubits while measurement, you know, process. But I mean, all of these things, in principle, you know, very straightforward, you know. I mean, it just need to be done, right? So, yeah.
Any more questions? Yes.
Yeah, so this morning from the discussion between Anatoly and Sylvain Caponi, we heard that numerically they cannot tell so far the answer to simple questions. For example, whether the gap vanishes in the thermodynamic limit or not for some simple frustrated magnetism systems. So do you think that this kind of question can be answered experimentally?
Well, okay, I think first this question has to be formulated carefully, right? But I can tell you that some of these discussions about, for example, MBL, they are extremely academic, in the following sense that you want to take the right order of limits and go to kind of infinite time.
It's not about MBL. It's just at equilibrium, the gap for, I don't remember which frustrated light is.
Okay, if you formulate it carefully, then I can tell you maybe where it can be solved or not. Yeah.
Well, I actually think whether we talk about MBL or this, I kind of disagree that this is academic, because it's like with glasses. You can say, oh, it's academic question whether this glass lives forever or not. But people ask this question. So if you want to answer it experimentally, you really have to tune yourself to close to the transition point and carefully study scaling. And in MBL community, no one did this, because of course, if you look into phase which lives, I don't know, for 10 minutes, how do you know whether it's like in your experimental millisecond? Of course, you never know it. But it's not impossible. Just I don't think experimentally the question was addressed. And I think with GAPT it's kind of similar, because the question is like, why do you care? So if you care in the sense that can you prepare the state which lives long enough that your experiment works, perfect, you are gapless. Maybe there is some other state which is there, but you cannot prepare it, it's irrelevant, there is no matrix elements between them and so on. So I kind of view it like that, because in a way you can ask, why do we care about ground states? Let's just take a step back. Actually, because nature, if we couple them to the bus, prepares us ground states, right, if we are cold enough, and they're stable states, right? So that's the only reason, at least in my opinion, we care about ground states as compared to other states. But if we have finite time experiment and we can prepare not a ground state but metastable state easily, then we should care about this metastable state.
Yeah, but it is, okay, that's maybe, it goes back to so I think these questions have to be very carefully formulated, right? Because, none of the systems are closed systems, right? We can make them more closed, and now actually with logical qubits, we can actually even sort of extend potentially the lifetime exponentially. But of course, logical qubits, then you sort of have to think about exactly what you do with them, because it's not it's not an analog problem anymore, right? But in general, you cannot, asking the question is, for the given phase, do you sort of, is your, what if does your lifetime scale with the system size, in this kind of exponential or down exponential? Will be very hard. But it is true that close to the phase transition, you could certainly study scaling, features. And the question is whether these different theories of possible MBL would give rise to interesting kind of predictions which are testable. And actually, I have not seen things. Yeah. Yeah, but it will not, in practice, it will not in practice, no. All of the systems will decohere, right? Asymptotically. They will decohere. There is nothing, the systems are not open systems, right? They are not closed systems.
Yes, but basically you're asking, if you increase disorder, do you reach asymptotic behavior?
Yeah, how the scaling will emerge. I think this is, if you formulate it carefully, maybe one can study, but it's not trivial.
Because
right?
if it's asymptotic behavior, you immediately see it. Of course, you cannot exclude that when you reach disorder, 10 million, something else will happen. But if you just see very good collapse and it kind of extends.
No, but look, there is for example, I don't want to kind of poo-poo, but there was experiments by Emmanuel's group, in 1 and 2 dimensions, probing this MBL. like,
Again,
but
like
what did we learn? I mean, I'm not so sure we learned a lot, right? I mean, I'm not,
numerically,
you know.
2D and 1D, they make no difference. It's like there was
Well,
some misinterpretation of Heinz theory.
but all of these experiments supposedly observed MBL, right? I mean, how do
No,
you?
I'm just saying, I observed that there is no glass, that this is like a truly stable phase, right?
Yeah.
So they observed a phase which has super slow lifetimes, right?
Well,
If you
it's
want
not
to
even,
say
you
that
cannot even tell a phase. They observe that some states relax very slowly, but you cannot conclude from that, right? And you cannot address the problem of existence in BL or not based on these experiments, based on specific.
I think you can. If you analyze scaling, you can.
Well, potentially, but not on what has been done, right? Yes. And there is, I mean, but one has to ask a question for what should be your coherence and so on. So it's like, you know, look, I think we don't disagree. But and I think these experiments will be, I mean, almost certainly hard, actually. But, yeah. Or maybe if you guys come up with a good idea, we will try, you know, I'm sure we'll try.
No, for glasses, people already did this. Like when they talked to Curie market, the same questions were asked in the 80s, and people came up with extremely careful experiments.
Right, but there they didn't care about but I didn't care whether the system is open or closed, right? They wanted, there's a system in thermal equilibrium, here is you want it like to be isolated. That's, you know.
Okay, so with that, maybe we should conclude. Thank you so much, Misha, for staying, and everybody.